The journey to understanding supermassive black holes begins not in the depths of space, but in the quiet studies of 18th century scholars who first dared to imagine objects from which even light could not escape. In 1783, a country rector named John Michell sat in his English parsonage, pondering Newton's laws of gravity and the nature of light. His calculations led him to a startling conclusion. If a star were massive enough and compact enough, its gravitational pull would be so strong that light itself would fall back to its surface like a stone thrown upward. He called these theoretical objects dark stars, bodies that would be invisible to our eyes, yet whose presence would be felt through their gravitational influence on nearby visible stars. Michell's idea was revolutionary for its time. He was suggesting that the universe might contain objects that we could never see directly, phantoms whose existence we could only infer through their effects on their surroundings. His paper, presented to the Royal Society of London, described how these dark stars might be detected by observing the orbital motions of visible companion stars. It was a prescient vision that would take nearly 2 centuries to fully realise. Just over a decade later, the French mathematician Pierre-Simon Laplace independently arrived at a similar conclusion. Working with the same Newtonian physics that governed the motion of planets and comets, Laplace calculated that if an object had the same density as Earth, but was 250 times larger in diameter, its escape velocity would exceed the speed of light. Like Michell before him, Laplace had stumbled upon the theoretical possibility of what we now call black holes, though the mathematics and physics of his time couldn't fully describe their true nature. These early ideas lay dormant for over a century, considered little more than mathematical curiosities. The scientific community of the 19th century had more pressing concerns, from understanding electromagnetic radiation to unravelling the mysteries of atomic structure. The concept of dark stars seemed like an abstract exercise with no connection to astronomical reality. After all, no one had observed anything remotely resembling these theoretical objects, and the technology to detect them was still generations away. Everything changed in 1915 when Albert Einstein published his general theory of relativity. This revolutionary framework here didn't just modify Newton's gravity, it completely reimagined it. Instead of thinking of gravity as a force that pulls objects together, Einstein showed that massive objects actually warp the fabric of space-time itself. Imagine space-time as a stretched rubber sheet. Place a bowling ball on it, and the sheet curves downward. Roll marbles nearby, and they spiral toward the bowling ball, not because of some invisible force, but because they're following the curved paths created by the bowling ball's weight. Einstein's equations were beautiful and elegant, but they also predicted some deeply unsettling possibilities. Just months after Einstein published his theory, Karl Schwarzschild, a German physicist serving on the Russian front during World War I, found an exact solution to Einstein's field equations. Working in the trenches between calculating artillery trajectories, Schwarzschild described the spacetime geometry around a perfectly spherical, non-rotating mass. His solution revealed something extraordinary and disturbing. At a certain distance from the centre of such a mass, which we now call the Schwarzschild radius or event horizon, space-time curved so severely that nothing, not even light, could escape. Schwarzschild's solution troubled even Einstein. The great physicist believed that nature would somehow prevent such extreme objects from forming. He thought that some unknown physical process would always intervene before matter could collapse to such incredible densities. For decades, many physicists shared Einstein's skepticism. The idea of a region of space from which nothing could escape seemed to violate fundamental principles about the conservation of information and the predictability of physical laws. The debate intensified in the 1930s when Subramanian Chandrasekhar, a young Indian physicist, calculated that stars above a certain mass would inevitably collapse at the end of their lives. Using the newly developed quantum mechanics and the theory of stellar structure, Chandrasekhar showed that when a star more massive than about 1.4 times our Sun exhausted its nuclear fuel, no known force could prevent it from collapsing indefinitely. His work was met with fierce resistance, particularly from Arthur Eddington, one of the most respected astrophysicists of the time. Eddington famously declared that there should be a law of nature to prevent a star from behaving in this absurd way. Despite the controversy, theoretical work on these collapsed objects continued. In 1939, Robert Oppenheimer and his student Hartland Snyder published a landmark paper describing the gravitational collapse of a massive star. They showed that from the perspective of an outside observer, time would appear to slow down near the collapsing star's surface, eventually seeming to freeze at the moment the star crossed its Schwarzschild radius. To someone falling with the collapsing matter, however, nothing special would happen at this boundary. They would continue falling toward the centre, ultimately being crushed by infinite gravitational forces at what mathematicians call a singularity. The term black hole itself didn't appear until 1967, coined by physicist John Wheeler during a conference in New York. Wheeler was searching for a more evocative name than gravitationally completely collapsed object, and his choice perfectly captured both the mystery and the defining characteristic of these objects. A black hole was black because no light could escape it, and it was a hole in the sense that anything falling in could never return. By the 1960s, the theoretical framework for understanding black holes was largely complete, but there was still no observational evidence for their existence. That began to change with the discovery of quasars in 1963. These quasi-stellar radio sources appeared as point-like objects in optical telescopes, but emitted enormous amounts of energy, more than entire galaxies. Their spectra showed huge redshifts, indicating they were billions of light-years away. For such distant objects to appear so bright, they had to be producing energy at rates that defied conventional explanation. Astronomers quickly realized that no ordinary stellar process could power quasars. Nuclear fusion, the energy source of stars, wasn't nearly efficient enough. The only mechanism that could convert matter to energy at the required rate was gravitational accretion onto a compact object. As matter spirals toward a black hole, it heats up through friction and compression, converting a significant fraction of its mass into energy before crossing the event horizon. This process is far more efficient than nuclear fusion, capable of converting up to 40% of infalling matter into radiation. The quasar discovery led theorists to propose that supermassive black holes, millions or billions of times more massive than our Sun, might lurk at the centres of galaxies. These wouldn't be the stellar mass black holes formed from collapsing stars, but something far grander in scale. The idea seemed fantastic, but it explained not only quasars but also the mysterious radio sources and jets observed emanating from the galactic centres. The search for direct evidence of supermassive black holes intensified in the 1970s and 80s. Astronomers developed new techniques to measure the velocities of stars and gas near galactic centres. If a supermassive black hole were present, nearby objects would orbit at tremendous speeds. The Doppler shift of their light would reveal these velocities, allowing astronomers to infer the mass of the central object. One of the first compelling cases came from observations of the galaxy Messier 87, a giant elliptical galaxy in the Virgo cluster. Using spectroscopy to measure the velocities of stars near its centre, astronomers found evidence for a central mass of several billion suns concentrated in a region smaller than our solar system. No known collection of stars could be packed so densely without collapsing into a black hole. The 1990s brought even more convincing evidence. The Hubble Space Telescope, launched in 1990, provided unprecedented resolution for observing galactic centers. Its observations revealed rapidly rotating disks of gas and dust around the centers of many galaxies, with velocities indicating the presence of supermassive black holes. Galaxy after galaxy showed the same pattern, suggesting that supermassive black holes were not rare exceptions, but common features of galactic architecture. Perhaps the most compelling evidence came from observations of our own galactic center. Using infrared telescopes to peer through the dust that obscures the Milky Way's core, astronomers began tracking individual stars orbiting an invisible object called Sagittarius A star. Over years and decades, they mapped out complete orbital paths. Some stars whipped around their orbits in just 15 years, reaching speeds of thousands of kilometers per second at their closest approach. The only explanation was a black hole of about 4 million solar masses sitting at the heart of our galaxy. This patient observational work earned Andrea Ghez and Reinhard Genzel the 2020 Nobel Prize in Physics. Their teams had provided irrefutable evidence that a supermassive black hole anchors our galaxy. What had begun as abstract mathematical speculation was now observational fact. Supermassive black holes were real, and they were everywhere. To truly understand supermassive black holes, we must first grasp what makes them different from their smaller stellar mass cousins, and what defines their extraordinary nature. A supermassive black hole is, at its most fundamental level, a region of spacetime where gravity has become so strong that it creates an inescapable prison for matter and light. But this simple description barely hints at the profound physics and cosmic significance of these objects. The defining boundary of any black hole is its event horizon, a surface in spacetime that marks the point of no return. For a non-rotating black hole, this horizon is perfectly spherical, its radius determined solely by the black hole's mass. The relationship is beautifully simple. Double the mass, and you double the radius. For a supermassive black hole of 1 billion solar masses, the event horizon would have a radius of about 3 billion kilometers, roughly 20 times the distance from Earth to the Sun. This might seem counterintuitively large, but it reveals something profound about supermassive black holes. Despite their immense gravity, the tidal forces at the event horizon of a supermassive black hole are actually quite gentle. If you were to fall feet first toward a stellar mass black hole, the gravitational pull on your feet would be catastrophically stronger than on your head, stretching you into what physicists grimly call spaghettification. But at the event horizon of 1 billion solar mass black hole, you would feel almost nothing unusual. The gradient of gravity across your body would be negligible. You could cross the event horizon without immediately realizing you had passed the point of no return. This gentleness at the horizon is one of the many paradoxes of supermassive black holes. They are simultaneously the most violent and serene objects in the universe. Their formation and growth involve processes of unimaginable energy, yet their event horizons can be crossed without drama. They power the brightest objects in the cosmos, yet they themselves emit no light. They destroy information that falls into them, yet they may preserve it in ways we're only beginning to understand. At the heart of every black hole, according to general relativity, lies a singularity, a point where the curvature of spacetime becomes infinite, and the known laws of physics break down. For a non-rotating black hole, this singularity is a point of zero volume and infinite density. For a rotating black hole, which is what we expect all real black holes to be, the singularity takes the form of a ring. But these descriptions are almost certainly incomplete. The singularity represents the frontier of our ignorance, the place where general relativity and quantum mechanics collide in ways we don't yet understand. The region around a supermassive black hole is anything but empty. It's a maelstrom of matter and energy, shaped by extreme gravity and electromagnetic forces. As matter falls toward the black hole, it doesn't plunge straight in. Conservation of angular momentum causes it to spiral inward, forming what we call an accretion disk. This disk is one of the most extreme environments in the universe, where matter is heated to millions or even billions of degrees, emitting radiation across the entire electromagnetic spectrum. The accretion disk around a supermassive black hole is a marvel of physics. As matter spirals inward, it must shed angular momentum to continue its journey toward the event horizon. This happens through viscous forces within the disk, essentially friction on a cosmic scale. The gravitational energy released as matter falls inward is converted to heat through these viscous processes, causing the disk to glow with fierce intensity. The inner regions of the disk, closest to the black hole, can reach temperatures exceeding 1 billion degrees, hot enough that the thermal radiation peaks in the X-ray portion of the spectrum. The efficiency of this process is staggering. When matter falls onto a non-rotating black hole, up to 6% of its rest mass can be converted to energy. For a maximally rotating black hole, this efficiency can reach 42%. Compare this to nuclear fusion in stars, which converts only about 0.7% of mass to energy, and you begin to understand why supermassive black holes can power such luminous phenomena as quasars. But not all the matter in an accretion disk is doomed to fall into the black hole. The intense radiation pressure from the hot inner disk can blow material away, creating powerful winds that carry matter and energy back into the host galaxy. These winds can reach velocities of thousands of kilometers per second and carry away more mass than actually falls into the black hole. They play a crucial role in regulating both black hole growth and star formation in the surrounding galaxy. Even more spectacular are the jets that some supermassive black holes produce. These narrow beams of matter and energy can extend for millions of light years, far beyond the boundaries of the host galaxy. The jets are launched from the region just outside the event horizon, where magnetic fields threading the accretion disk and the spinning black hole itself can accelerate particles to speeds approaching that of light. The exact mechanism of jet formation remains one of the active areas of black hole research, but it likely involves the extraction of rotational energy from the black hole itself through a process called the Blandford-Znajek mechanism. The spin of a supermassive black hole is one of its fundamental properties, as important as its mass. A black hole can rotate at speeds approaching the speed of light at its event horizon, and this rotation profoundly affects the space-time around it. A spinning black hole drags space-time around with it, a phenomenon called frame dragging, or the lens-thirring effect. Near a rapidly rotating supermassive black hole, space-time itself is twisted into a whirlpool-like configuration. Any object near the black hole is carried along by this swirling space-time, like a leaf caught in a whirlpool. This rotation creates a special region around the black hole called the ergosphere, which extends beyond the event horizon. The ergosphere is a place where space-time is dragged around so forcefully that nothing can remain stationary relative to distant stars. Everything must rotate with the black hole. Remarkably, it's theoretically possible to extract energy from a rotating black hole by exploiting the properties of the ergosphere, a process known as the Penrose process. A particle entering the ergosphere can split in two, with one part falling into the black hole and the other escaping with more energy than the original particle possessed. The temperature of a black hole might seem like a contradiction. After all, if nothing can escape from inside the event horizon, how can a black hole have a temperature? The answer came from Stephen Hawking's groundbreaking work in the 1970s. By applying quantum mechanics to black hole physics, Hawking discovered that black holes do emit radiation, now called Hawking radiation. This radiation arises from quantum fluctuations near the event horizon, where virtual particle pairs can be separated by the black hole's gravity, with one falling in and the other escaping. For stellar mass black holes, Hawking radiation is negligibly weak, and the black hole's temperature is less than 1/1000th of a degree above absolute zero. But for supermassive black holes, the situation is even more extreme. The temperature of a black hole is inversely proportional to its mass, so supermassive black holes are the coldest objects in the universe. With temperatures so low, they're essentially impossible to measure. A billion solar mass black hole would have a temperature of about 60 trillionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe. This means that supermassive black holes are actually gaining mass from the cosmic microwave background faster than they're losing it through Hawking radiation. Only in the unimaginably distant future, when the universe has expanded and cooled far below its current temperature, will supermassive black holes begin to evaporate through Hawking radiation. The timescale for this evaporation is so vast that it dwarfs every other timescale in astronomy. A supermassive black hole of 1 billion solar masses would take about 10 to the 100th power years to evaporate completely, a number so large that it has no meaningful comparison to anything in human experience. The information paradox is perhaps the deepest puzzle associated with black holes. When matter falls into a black hole, what happens to the information it carries? According to quantum mechanics, information must be preserved, yet general relativity suggests that anything falling into a black hole is lost forever, crushed at the singularity. This contradiction has spawned decades of theoretical research and debate. Some physicists propose that information is encoded on the event horizon itself, in a kind of holographic principle where the three-dimensional information about infalling matter is preserved on the two-dimensional surface of the horizon. Others suggest that information might be released in highly scrambled form through Hawking radiation, though how this could work in detail remains mysterious. Recent theoretical work has even suggested that black holes might not have event horizons in the classical sense. Some theories propose that quantum effects might create a firewall at the horizon, a region of extreme energy that would destroy anything attempting to cross. Other theories suggest that the horizon might be replaced by a fuzzball of quantum strings, or that black holes might actually be gravastars with no true horizon at all. While these ideas remain highly speculative, they illustrate how much we still have to learn about the fundamental nature of black holes. The origin story of supermassive black holes is one of the great mysteries of modern astrophysics, a cosmic puzzle that takes us back to the universe's earliest epochs. Unlike stellar mass black holes, which form from the collapse of massive stars in a process we understand reasonably well, supermassive black holes present a paradox. They appear to have existed when the universe was less than 1 billion years old. Yet growing a black hole to supermassive size through conventional means should take much longer. How did these giants form so quickly? The challenge becomes clear when we consider the numbers. Observations of distant quasars reveal supermassive black holes of billions of solar masses already in place when the universe was only 700 million years old. Starting from a stellar mass seed of perhaps 10 or 20 solar masses, growing to 1 billion solar masses would require continuously accreting matter at the maximum theoretical rate for the entire age of the universe at that time. This seems impossibly efficient, especially considering that black hole growth is self-limiting. As matter falls toward a black hole and heats up, the radiation pressure pushes back against infalling material, creating what astronomers call the Eddington limit, a maximum rate at which a black hole can grow. Three main scenarios have emerged to explain the rapid formation of supermassive black holes, each with its own compelling evidence and challenging problems. These aren't mutually exclusive. Different supermassive black holes might have formed through different pathways, or multiple mechanisms might have operated together. The first scenario involves massive seeds from the universe's first generation of stars, known as population 3 stars. These primordial giants formed from pristine hydrogen and helium, unpolluted by heavier elements that hadn't yet been created. Without heavy elements to help radiate away heat, these first stars could grow to enormous sizes, perhaps hundreds or even thousands of times the mass of our Sun. When such massive stars collapsed at the end of their brief lives, they would have formed black holes of hundreds of solar masses, giving supermassive black holes a head start in their growth. These population 3 stars would have been extraordinary objects, forming in dark matter halos. When the universe was only 100 million years old, they would have been isolated giants, each one alone in its small protogalaxy. Their surfaces would have been incredibly hot, perhaps 50,000 degrees or more, causing them to emit most of their light in the ultraviolet. This intense radiation would have begun the process of reionizing the universe, ending the cosmic dark ages that followed the Big Bang. When these massive stars exhausted their nuclear fuel after just a few million years, their collapse would have been catastrophic. The most massive ones might have collapsed directly to black holes without exploding a supernova, preserving all their mass for the black hole seed. These direct collapse black holes could have been born with masses of hundreds or even thousands of solar masses, already far larger than typical stellar mass black holes formed today. But even starting with such massive seeds, growing to supermassive size remains challenging. The black holes would need to accrete matter at near the Eddington limit for hundreds of millions of years. They would need a steady supply of gas, which might be disrupted by their own radiation or by nearby star formation. Computer simulations suggest that while this pathway is possible, it requires rather special conditions that might not have been common in the early universe. The second scenario bypasses stellar evolution entirely through what astronomers call direct collapse black holes. In this model, massive gas clouds in the early universe collapse directly to form black holes of 10,000 to 100,000 solar masses. This can happen only under very specific conditions. The gas cloud must be massive enough and dense enough to overcome its own pressure, but it must also avoid fragmenting into stars during the collapse. The key to direct collapse is preventing the gas from cooling too efficiently. In normal star formation, gas cools by radiating away energy, allowing it to fragment into clumps that become individual stars. But if the gas is kept hot, perhaps by intense ultraviolet radiation from nearby galaxies, it can't fragment. Instead, the entire cloud collapses monolithically, forming a single supermassive object. This process would have been spectacular to witness, had anyone been around to see it. A gas cloud of millions of solar masses, perhaps 1,000 light-years across, would begin to contract under its own gravity. As it collapsed, it would spin faster, like an ice skater pulling in her arms. The gas would heat up from compression, glowing first in infrared, then visible light, then ultraviolet. The collapse would accelerate, with the inner regions falling faster than the outer ones, creating a dense, hot core surrounded by an envelope of infalling gas. At some point, the core would become so dense that general relativistic effects would take over. The collapse would become unstoppable, creating a black hole at the center, while gas continued to rain down from the envelope. Within perhaps 100,000 years, a black hole of 10,000 to 100,000 solar masses would be born, already intermediate in mass between stellar and supermassive black holes. Direct collapse black holes solve the timescale problem elegantly. Starting with such massive seeds, growing to billions of solar masses becomes much more feasible. The black holes would still need to accrete efficiently, but they wouldn't need to maintain the absolute maximum growth rate for their entire lives. Simulations suggest that direct collapse could have occurred in the early universe, particularly in regions where gas was prevented from cooling by strong ultraviolet radiation fields. The third scenario involves dense stellar clusters in the centers of early galaxies. In this model, stars form normally but are packed so densely that they begin to collide and merge. Through runaway collisions, a very massive star forms at the cluster's center, which then collapses to form an intermediate mass black hole. This black hole continues to grow by swallowing stars and gas from the surrounding cluster. This process would unfold in the nuclear star clusters that we observe at the centers of many galaxies today. These clusters contain millions of stars packed into regions just a few light years across. The stellar density is so high that stars pass within a few astronomical units of each other, close enough for their gravitational interactions to gradually sink the most massive stars toward the center through a process called dynamical friction. Once the massive stars congregate at the center, collisions become inevitable. When two massive stars collide, they can merge to form an even more massive star. This process can run away, with the merged star sinking further into the center and colliding with more stars. Eventually, a star of thousands of solar masses forms, so massive that it's unstable against gravitational collapse. When it finally collapses, it forms a black hole that already has a significant head start towards supermassive status. The cluster environment provides a ready supply of fuel for the growing black hole. Stars on unfortunate orbits are torn apart by tidal forces, their gas feeding the black hole. The dense gas in the cluster center provides additional fuel. As the black hole grows, its gravitational influence extends further into the cluster, allowing it to capture and consume more stars and gas. Each of these formation scenarios predicts different properties for the resulting supermassive black holes. Direct collapse black holes should be born with very little spin, while black holes formed from population 3 stars might be rapidly rotating. Black holes grown in dense clusters should be surrounded by the remnants of their formation environment, perhaps observable as nuclear star clusters today. The early growth phase of supermassive black holes, regardless of their formation mechanism, would have been a period of extreme activity. These adolescent giants would have been surrounded by dense gas clouds, feeding at prodigious rates. Their accretion disks would have blazed with the light of millions of suns, creating the first quasars. Jets launched from their poles would have carved cavities in the surrounding gas, perhaps triggering or suppressing star formation in their host galaxies. The growth of supermassive black holes wasn't a smooth, continuous process. It was likely episodic, with periods of rapid growth alternating with relative quiescence. When gas was plentiful, the black hole would feed voraciously, shining as a quasar. But this intense radiation would eventually blow away the surrounding gas, cutting off the food supply. The black hole would then enter a quiet phase until new gas arrived, perhaps from a galaxy merger or from cooling of hot gas in the galaxy's halo. Computer simulations of early universe conditions reveal the complexity of supermassive black hole formation. The process involves an intricate interplay of dark matter dynamics, gas physics, radiation transport, and star formation. Small changes in initial conditions can lead to vastly different outcomes. Some regions of the universe might have formed supermassive black holes early and efficiently, while others might have formed them slowly or not at all. The role of dark matter in supermassive black hole formation is still being explored. Dark matter halos provided the gravitational wells in which the first galaxies and black holes formed. The properties of these halos, their mass, concentration, and merger history influenced when and how supermassive black holes could form. Some theories even propose that supermassive black holes might have formed from the collapse of dark matter itself, though this remains highly speculative. Recent observations are providing new clues about supermassive black hole formation. The James Webb Space Telescope has detected surprisingly massive black holes in the early universe, some appearing overmassive relative to their host galaxies compared to the present-day relationship. This suggests that black holes might have formed before their host galaxies were fully assembled, or that they grew more efficiently in the early universe than previously thought. The discovery of intermediate mass black holes with masses between hundreds and hundreds of thousands of solar masses provides potential missing links in the formation story. These objects might be the descendants of the original seeds, caught in the act of growing towards supermassive status. Finding and studying more intermediate mass black holes could help us understand which formation scenarios actually operated in nature. The chemical composition of gas around supermassive black holes also holds clues to their origin. Different formation scenarios predict different metallicity patterns in the gas. Direct collapse black holes should be surrounded by relatively pristine gas, while black holes grown in stellar clusters should show chemical enrichment from stellar processing. Future observations with next-generation telescopes might be able to detect these chemical signatures. To truly appreciate the magnificent complexity of a supermassive black hole system, we must examine its anatomy piece by piece, from the enigmatic singularity at its heart to the vast jets that can stretch across millions of light years. Each component plays a crucial role in the black hole's interaction with its environment, creating a dynamic system that shapes entire galaxies. At the very centre lies the singularity, though calling it the centre is somewhat misleading. The singularity isn't really a place in the conventional sense, but rather a moment in time, the future endpoint for anything that crosses the event horizon. According to general relativity, the singularity is where space-time curvature becomes infinite, where densities exceed any meaningful measure, and where our current physics breaks down completely. For a rotating black hole, which all real supermassive black holes are believed to be, the singularity takes the form of a ring rather than a point. Though this description, too, is likely just a placeholder for physics we don't yet understand. Surrounding the singularity is the event horizon, the defining boundary of the black hole proper. For a supermassive black hole of 1 billion solar masses, this invisible sphere would have a radius of about 3 billion kilometers. The event horizon isn't a physical surface you could stand on or touch. It's simply the boundary in space-time beyond which events cannot affect the outside universe. An astronaut crossing the event horizon of a supermassive black hole wouldn't feel anything special at that moment. No force, no barrier, no sudden change. They would simply pass a point of no return, after which all paths lead inexorably toward the singularity. The size of the event horizon depends only on the black hole's mass and spin. A rapidly rotating black hole has a smaller event horizon than a non-rotating one of the same mass, as the rotation effectively compresses the horizon. At maximum theoretical spin, the event horizon radius is half that of a non-rotating black hole. This might seem counterintuitive, but it reflects the profound way rotation warps spacetime around the black hole. Just outside the event horizon of a rotating black hole lies one of the most exotic regions in the universe, the ergosphere. This oblate spheroid-shaped region is where space-time itself is dragged around by the black hole's rotation so forcefully that nothing can remain stationary relative to the distant stars. The name comes from the Greek word ergon, meaning work, because it's theoretically possible to extract energy from this region. The outer boundary of the ergosphere touches the event horizon at the poles, but extends well beyond it at the equator, creating a region where space itself swirls like water going down a drain. Within the ergosphere, particles and light must rotate with the black hole, carried along by the twisted space-time. This frame-dragging effect is so strong that even light travelling against the rotation direction is swept along. The ergosphere is where some of the most energetic processes around black holes occur, possibly including the launching of jets and the extraction of rotational energy from the black hole itself. Moving outward from the ergosphere, we encounter the innermost stable circular orbit, or ISCO, a critical boundary for matter orbiting the black hole. Inside the ISCO, no stable orbits exist. Any particle or gas that ventures inside this radius will inexorably spiral into the black hole. The location of the ISCO depends dramatically on the black hole's spin. For a non-rotating black hole, it lies at 3 times the event horizon radius. But for a maximally rotating black hole spinning in the same direction as the orbiting matter, the ISCO shrinks to just half the horizon radius, allowing matter to orbit much closer to the black hole before taking the final plunge. This difference has profound implications for the accretion disk that forms around feeding supermassive black holes. The closer matter can orbit stably, the more gravitational energy it releases before falling in, making rapidly rotating black holes much more efficient at converting matter to energy. This efficiency difference can be detected in the spectrum of light emitted by the accretion disk, providing one way astronomers can measure black hole spin. The accretion disk itself is one of the most extreme environments in the universe. As matter spirals toward the black hole, conservation of angular momentum forces it into a rotating disk, much like water swirling down a drain. But this cosmic drain operates under conditions that push matter to its limits. The inner edge of the disk, near the ISCO, can reach temperatures exceeding 1 billion degrees, hot enough that the thermal radiation peaks in the X-ray band. The disk is also incredibly thin relative to its width, perhaps only a few percent as thick as its radius, maintained in this configuration by the balance between the black hole's gravity pulling inward and radiation pressure pushing outward. The physics within the accretion disk is remarkably complex. Matter must lose angular momentum to spiral inward, which happens through viscous processes that are still not fully understood. Magnetic fields threading the disk play a crucial role, creating turbulence through the magneto-rotational instability. This turbulence transports angular momentum outward, allowing matter to flow inward while heating the disk through friction-like processes. The accretion disk isn't uniform, but shows distinct regions with different physical conditions. The outer disk, hundreds or thousands of gravitational radii from the black hole, is relatively cool and thin, emitting primarily an infrared and visible light. As we move inward, the disk becomes hotter and thicker, with the emission shifting to ultraviolet and soft X-rays. The inner disk, within a few tens of gravitational radii, is a hellish environment where matter is heated to such extreme temperatures that atoms are completely ionized, creating a plasma of bare nuclei and electrons. In this inner region, radiation pressure becomes so intense that it can exceed the gravitational pull of the black hole for lighter particles, creating a powerful wind that flows away from the disk. These disk winds can carry away more mass than actually falls into the black hole, playing a crucial role in regulating both black hole growth and star formation in the surrounding galaxy. The winds emerge from the disk surface at various angles, creating a complex outflow pattern that can extend for thousands of light years. Above and below the accretion disk lies the corona, a region of extremely hot, tenuous plasma that emits hard X-rays. The corona's exact structure remains one of the mysteries of black hole physics. It might form a sandwich-like layer above and below the disk, or it might be concentrated near the black hole's poles. The temperature in the corona can exceed 1 billion degrees, hot enough that electrons are moving at speeds close to the speed of light. These relativistic electrons scatter photons from the disk, boosting their energy through a process called inverse Compton scattering, creating the hard X-ray emission we observe. The corona plays a crucial role in our ability to study black holes. X-rays from the corona illuminate the inner accretion disk, causing iron atoms in the disk to fluoresce. The resulting iron emission lines, distorted by the black hole's gravity and the disk's motion, create a characteristic spectral signature that allows astronomers to map the space-time geometry near the event horizon. These observations have provided some of our best evidence for the existence of event horizons and have allowed measurements of black hole spin. Surrounding the entire accretion system is the broadline region, clouds of gas extending from hundreds to thousands of light days from the black hole. These clouds orbit the black hole at velocities of thousands of kilometers per second, heated and ionized by radiation from the accretion disk. The Doppler broadening of emission lines from these clouds gives the region its name and provides a way to measure the black hole's mass through reverberation mapping, a technique that measures the time delay between variations in the continuum emission and the response of the line-emitting clouds. Further out still, at distances of light years from the black hole, lies the narrow line region. Here, gas clouds move more slowly, producing narrower emission lines in spectra. The narrow line region can extend for thousands of light years, its gas ionized by the intense radiation from the central engine. The structure of this region is complex, with gas distributed in clouds, filaments, and shells, shaped by radiation pressure, winds from the accretion disk, and jets from the black hole. Perhaps the most spectacular component of some supermassive black hole systems are the jets, twin beams of matter and energy that can extend for millions of light years. Not all supermassive black holes produce jets, and the exact conditions required for jet formation remain debated. The jets appear to be launched from the region very close to the black hole, possibly from the ergosphere itself, where magnetic fields anchored in the accretion disk or threaded through the event horizon can accelerate particles to near light speed. The jet launching mechanism likely involves the twisting of magnetic field lines by the black hole's rotation and the differential rotation of the accretion disk. As field lines are wound up like springs, they can snap and reconnect, releasing enormous amounts of energy that accelerates particles along the black hole's rotation axis. This process, called the Blandford-Znajek mechanism, when the fields thread the event horizon, can extract rotational energy from the black hole itself, gradually slowing its spin while powering the jets. The jets themselves are remarkable physics laboratories. They maintain their collimation over enormous distances, staying narrow despite travelling through varying environments. The matter in jets moves at speeds exceeding 99% of the speed of light, creating relativistic effects that boost their apparent brightness when pointed toward us. The jets contain a mixture of electrons, positrons, and possibly protons, along with magnetic fields that help maintain their structure. As jets propagate through space, they interact with the surrounding medium, creating a variety of structures. Where the jet rams into intergalactic gas, it creates hotspots, regions of intense emission where kinetic energy is converted to radiation. The jets inflate giant lobes of radio-emitting plasma, cavities in the intergalactic medium that can persist for millions of years after the jets turn off. These radio lobes can be hundreds of times larger than the host galaxy, making them some of the largest coherent structures in the universe. The magnetic field configuration around a supermassive black hole is crucial to its behavior, but remains poorly understood. Magnetic fields are thought to thread the entire system, from the event horizon through the accretion disk and out into the jets. These fields help transport angular momentum in the disk, launch and collimate jets, and accelerate particles to high energies. The strength and configuration of these fields can vary dramatically, potentially explaining why some black holes are radio loud with prominent jets while others are radio quiet. Recent simulations suggest that the magnetic field near the black hole can become so strong that it significantly affects the accretion flow. In what's called a magnetically arrested disk, the magnetic pressure near the black hole becomes comparable to the gas pressure, disrupting the smooth inward flow of matter. This can lead to episodic accretion, with periods of rapid infall alternating with times when the magnetic field holds matter back. The entire supermassive black hole system is surrounded by a torus of molecular gas and dust, extending from a few light years to hundreds of light years from the black hole. This dusty torus plays a crucial role in the appearance of active galactic nuclei. When we view the system edge-on, the torus blocks our direct view of the accretion disk and broadline region, creating what we classify as a Type II active galactic nucleus. When viewed face-on, we can see directly into the central engine, observing a Type I AGN or quasar. The torus isn't a smooth, uniform structure, but rather a clumpy, dynamic region with gas clouds orbiting the black hole. Radiation pressure from the accretion disk puffs up the inner edge of the torus, while gravity and cloud collisions cause material to flow inward, feeding the black hole. The torus also reprocesses radiation from the accretion disk, absorbing ultraviolet and X-ray photons and re-emitting them in the infrared, creating the characteristic infrared excess observed in many active galactic nuclei. The growth of a supermassive black hole through accretion is one of the most efficient energy conversion processes in the universe, a cosmic engine that transforms infalling matter into radiation with remarkable efficiency. Understanding how these giants feed reveals not only the physics of extreme gravity, but also the mechanisms that regulate galaxy evolution across cosmic time. When matter approaches a supermassive black hole, it rarely falls directly in. Any slight angular momentum, even the tiniest deviation from a perfectly radial trajectory, causes the matter to orbit the black hole rather than plunging straight toward it. As more material arrives, collisions between particles cause them to lose energy and angular momentum, gradually spiraling inward while forming a rotating disk. This accretion disk becomes the primary feeding mechanism for the black hole, a cosmic conveyor belt delivering matter to the event horizon. The efficiency of this process is extraordinary. As matter spirals through the accretion disk, gravitational potential energy is converted to kinetic energy, then to thermal energy through viscous processes in the disk. For a non-rotating black hole, about 6% of the rest mass energy of infalling matter can be radiated away before it crosses the event horizon. For a maximally rotating black hole with matter orbiting in the same direction, this efficiency can reach 42%. Compare this to nuclear fusion in stars, which converts only about 0.7% of mass to energy, and you begin to understand why accreting black holes can shine so brilliantly. The journey of a gas cloud falling toward a supermassive black hole is a dramatic transformation. Starting perhaps thousands of light years from the black hole, the gas might be cool and relatively diffuse, held up by its own pressure and angular momentum. As it loses angular momentum through various processes, magnetic braking, viscous torques, or gravitational interactions with stars, it begins to spiral inward. The gas heats up through compression and shocks, beginning to glow in infrared light. As the gas continues inward, entering the outer regions of the accretion disk, the temperature rises to thousands of degrees. Atoms begin to lose their electrons, creating a partially ionized plasma. The disk's surface glows with visible light, perhaps appearing orange or white-hot to an observer. Magnetic fields threading the disk create turbulence through the magneto-rotational instability, generating the viscosity that allows the gas to continue spiraling inward while transporting angular momentum outward. Approaching the inner disk within 100 gravitational radii of the black hole, conditions become truly extreme. Temperatures soar to millions of degrees, and the gas becomes fully ionized. The disk emits primarily in ultraviolet and X-rays, with luminosities that can exceed the combined light of 1 trillion stars. The radiation pressure from this intense emission becomes comparable to, or even exceeds, the black hole's gravitational pull, creating a delicate balance that regulates the accretion rate. This balance defines what astronomers call the Eddington limit, named after Sir Arthur Eddington, who first calculated it for stars. When a black hole accretes at the Eddington rate, the outward radiation pressure exactly balances the inward gravitational pull for fully ionized hydrogen. For a billion solar mass black hole, the Eddington luminosity is about 10 to the 47 ergs per second, equivalent to the light of 20 trillion suns. If the black hole tries to accrete faster, producing more radiation, the increased radiation pressure blows material away, reducing the accretion rate. This self-regulation means black holes cannot grow arbitrarily fast. However, nature finds ways around this limit. If the accreting material is very dense, or if the geometry of the inflow is not a thin disk, super-Eddington accretion becomes possible. In these cases, the radiation might be trapped in the flow, advected into the black hole before it can escape, or beamed in directions that don't oppose the infall. Some theories suggest that early supermassive black holes might have grown through extended periods of super-Eddington accretion, allowing them to reach enormous masses in the limited time available. The accretion flow isn't always a geometrically thin disk. When the accretion rate is very low, the gas density becomes so small that particles rarely collide. Without collisions to thermalize the energy, the gas remains hot and forms a geometrically thick, optically thin flow called an advection-dominated accretion flow, or a DAF. In this state, most of the gravitational energy is advected into the black hole rather than radiated away, making the black hole much dimmer than expected from its accretion rate. This might explain why many supermassive black holes, including our own Sagittarius A star, are surprisingly faint despite having plenty of gas in their vicinity. The feeding process isn't steady, but often occurs in episodes triggered by various events. A molecular cloud wandering too close to the black hole might be captured and consumed over thousands of years. A star passing near the black hole might be torn apart by tidal forces in what astronomers call a tidal disruption event, providing a sudden feast that causes the black hole to flare dramatically in brightness. Galaxy mergers can drive large amounts of gas toward the centre, triggering intense accretion episodes that we observe as quasars. Tidal disruption events are particularly dramatic feeding events. When a star ventures too close to a supermassive black hole, the gravitational force on the near side of the star exceeds that on the far side, by such a margin that the star is literally pulled apart. The point where this occurs, called the tidal radius, depends on the black hole's mass and the star's density. For a solar-type star and a million solar mass black hole, the tidal radius is about 50 times the event horizon radius. The destruction of the star unfolds over just a few hours, but the feeding process continues for months or years. About half the star's material is ejected from the system entirely, while the other half forms an accretion disk around the black hole. This sudden influx of material causes the black hole to brighten dramatically, sometimes increasing its luminosity by factors of thousands or more. The light curve of a tidal disruption event has a characteristic shape, rising rapidly to peak brightness, then declining as a power law as the material is consumed. These events provide unique laboratories for studying black hole feeding. Because we know roughly how much material is involved, half a stellar mass, and can observe the entire feeding process from start to finish, tidal disruption events allow us to test our theories of accretion physics in detail. They also provide a way to discover and study otherwise quiescent supermassive black holes that don't have permanent accretion disks. The fuel supply for supermassive black holes comes from various sources. In the local universe, most comes from gas within the host galaxy, either from stellar winds of aging stars, cooling of hot gas in the galaxy's halo, or gas driven inward by gravitational instabilities. The rate at which gas is supplied to the black hole depends on many factors. The galaxy's gas content, its dynamical state, the presence of bars or spiral arms that can drive gas inward, and feedback from the black hole itself. Feedback is a crucial aspect of the feeding process, creating a self-regulating cycle that links black hole growth to galaxy evolution. As the black hole feeds and grows, it releases enormous amounts of energy. This energy heats and expels gas from the galaxy's center, cutting off the black hole's food supply. The black hole then enters a quiet phase until gas can cool and fall back toward the center, starting the cycle anew. This feedback cycle helps explain the observed correlations between black hole mass and galaxy properties. The feedback can take many forms. Radiation from the accretion disk heats nearby gas, preventing it from cooling and forming stars. Winds launched from the disk can sweep gas out of the galaxy entirely. Jets can inject energy into the surrounding medium on scales far larger than the galaxy itself. Each feedback mechanism operates on different scales and timescales, creating a complex regulatory system that we're still working to understand. Computer simulations of black hole feeding have revealed the intricate dynamics of the accretion process. These simulations must account for gravity, magnetic fields, radiation transport, and gas dynamics across an enormous range of scales, from the event horizon to the outer reaches of the galaxy. They show that accretion is often chaotic and variable, with the accretion rate fluctuating on timescales from minutes to millions of years. The variability of accreting supermassive black holes provides another window into the feeding process. By monitoring how their brightness changes over time, astronomers can map out the structure of the accretion flow. Rapid variability on timescales of hours or days must come from the inner accretion disk near the black hole. Slower variations might reflect changes in the fuel supply or the propagation of instabilities through the disk. The spectral energy distribution of accreting black holes, how their emission is distributed across different wavelengths, tells us about the physical conditions in different parts of the system. The infrared emission comes from the dusty torus, the optical and ultraviolet from the outer and middle accretion disk, the X-rays from the inner disk and corona, and the radio from jets or winds. By observing across the electromagnetic spectrum, we can piece together a complete picture of the feeding process. The relationship between supermassive black holes and their host galaxies is one of the most profound discoveries in modern astrophysics, revealing these gravitational giants not as mere passengers, but as active architects of galactic structure and evolution. Despite occupying a volume smaller than our solar system, supermassive black holes influence regions millions of times larger, shaping the destinies of entire galaxies through a complex interplay of gravity, radiation, and mechanical feedback. The discovery of fundamental correlations between black hole mass and galaxy properties provided the first hints of this deep connection. The mass of a supermassive black hole correlates remarkably well with the velocity dispersion of stars in the galaxy's bulge, a relationship known as the M-sigma relation. Black hole mass also correlates with the mass of the galactic bulge itself, typically comprising about 0.1 to 0.2% of the bulge mass. These relationships hold across a wide range of galaxy types and masses, from modest spiral galaxies to giant ellipticals, suggesting a fundamental link between black hole growth and galaxy formation. What makes these correlations so remarkable is the vast difference in scales involved. The black hole's gravitational influence extends only to about a parsec from the galaxy center, yet the stellar bulge extends for thousands of parsecs. How can such a compact object influence such a large volume? The answer lies in the enormous energy released during black hole growth. When a supermassive black hole accretes matter, it can liberate energy equivalent to billions of supernovae. This energy, injected into the surrounding galaxy through radiation, winds and jets, can profoundly affect star formation and gas dynamics throughout the entire system. The coevolution of black holes and galaxies appears to begin in the early universe. Observations of distant quasars show that the black hole galaxy correlations were already in place when the universe was less than 1 billion years old. This suggests that whatever processes establish these relationships operate quickly and efficiently. The growth of the black hole and the assembly of the stellar bulge must be linked from the very beginning, not coupled later through some secondary process. Galaxy mergers play a crucial role in this coevolution. When two galaxies collide and merge, their supermassive black holes eventually sink to the center of the merged system through dynamical friction. The merger drives gas toward the center, triggering both intense star formation and black hole accretion. This dual growth phase, where both the stellar bulge and black hole grow rapidly, helps establish and maintain the observed correlations. During a galaxy merger, the dynamics are spectacular and chaotic. As the galaxies approach each other, tidal forces distort their shapes, drawing out long streams of stars and gas called tidal tails. Gas clouds collide at high speeds, triggering shock waves that compress the gas and spark intense bursts of star formation. These starburst regions glow brilliantly in infrared light, earning merging galaxies the name luminous infrared galaxies, or LIRGs. Meanwhile, gravitational torques from the distorted galactic structure drive gas toward the center of each galaxy, feeding the supermassive black holes. As the galaxies continue to merge, the black holes grow rapidly, potentially entering a quasar phase where they outshine the entire galaxy. The energy released during this phase can be so intense that it eventually expels much of the remaining gas from the galaxy, shutting down both star formation and further black hole growth. This self-regulation helps explain why black holes don't grow indefinitely and why the black hole galaxy correlations are so tight. The feedback from supermassive black holes takes multiple forms, each operating on different scales and timescales. Radiative feedback occurs when photons from the accretion disk interact with surrounding gas. In the immediate vicinity of the black hole, intense radiation can ionize and heat gas to millions of degrees, preventing it from cooling and forming stars. On larger scales, radiation pressure can drive powerful winds that sweep gas out of the galaxy entirely. These radiative winds have been observed in many quasars, with velocities reaching thousands or even tens of thousands of kilometers per second. The winds carry enormous amounts of energy and momentum, capable of ejecting more gas than the galaxy's entire interstellar medium. When such winds sweep through a galaxy, they can completely transform its evolution, converting a gas-rich, star-forming galaxy into a gas-poor, quiescent system where star formation has ceased. Mechanical feedback from jets provides another pathway for black holes to influence their surroundings. The jets inject energy directly into the intergalactic medium, inflating giant bubbles of hot plasma that can be observed in X-rays. These bubbles or cavities can be hundreds of thousands of light-years across, far larger than the host galaxy itself. The energy required to inflate such cavities is enormous, equivalent to the total energy output of billions of supernovae. In galaxy clusters, jet feedback plays a crucial role in solving what astronomers call the cooling flow problem. X-ray observations show that the hot gas in cluster centers should be cooling rapidly, with hundreds of solar masses per year condensing out of the hot phase. This cooling gas should then form stars at a prodigious rate. Yet most galaxy clusters show much lower star formation rates than expected. The solution appears to be heating from the central supermassive black hole's jets, which inject enough energy to offset the cooling, maintaining the gas in a hot, diffuse state. The feedback process creates a regulatory cycle that links black hole activity to the gas supply in the galaxy. When gas is plentiful, the black hole feeds and grows, releasing energy that heats and expels gas from the galaxy center. This reduces the gas supply, causing the black hole to enter a quiescent phase. Over millions of years, gas cools and flows back toward the center, triggering another episode of black hole activity. This cycle, operating over cosmic time, maintains the observed correlations between black hole and galaxy properties. The impact of supermassive black holes extends beyond their immediate host galaxies. In galaxy clusters, the central black hole can influence the evolution of hundreds of neighboring galaxies. By heating the intracluster medium, the black hole prevents cooling and condensation of gas that would otherwise be available for star formation in cluster galaxies. This helps explain why galaxies in cluster centers tend to be red and dead, dominated by old stars with little ongoing star formation. Computer simulations have been instrumental in understanding black hole galaxy coevolution. Modern simulations can follow the formation and evolution of galaxies from the early universe to the present day, including the growth of supermassive black holes and their feedback effects. These simulations reproduce many observed properties of galaxies, including the black hole galaxy correlations, only when black hole feedback is included. Without feedback, simulated galaxies form too many stars and grow too massive compared to observed galaxies. The simulations reveal that feedback must be both powerful and gentle. Too much feedback, and galaxies are completely stripped of gas, unable to form any stars. Too little, and galaxies become overly massive with excessive star formation. The balance must be just right, a Goldilocks scenario that maintains galaxies in a state of regulated growth. This fine-tuning might seem contrived, but it emerges naturally from the physics of black hole accretion and feedback. Different types of galaxies show different relationships with their central black holes. Elliptical galaxies, which are generally gas-poor with little ongoing star formation, tend to have the most massive black holes relative to their stellar mass. Their black holes are usually quiescent, accreting at very low rates. Spiral galaxies, like our Milky Way, have smaller black holes relative to their total mass, and these black holes are often mildly active, accreting gas at modest rates. The most extreme examples of black hole influence are found in massive galaxy clusters, where the central galaxy often hosts a supermassive black hole of 10 billion solar masses or more. These ultramassive black holes have grown through multiple galaxy mergers and prolonged accretion over cosmic time. Their influence extends throughout the cluster, affecting the evolution of hundreds or thousands of galaxies. Recent observations have revealed surprising aspects of black hole galaxy coevolution. Some galaxies in the early universe appear to have black holes that are overly massive compared to their stellar bulges, suggesting that black hole growth might sometimes precede galaxy assembly. Other systems show evidence for multiple supermassive black holes, remnants of galaxy mergers where the black holes haven't yet coalesced. These observations challenge our models and suggest that coevolution might be more complex and varied than previously thought. The role of supermassive black holes in galaxy evolution extends to the regulation of dark matter halo growth. Through their feedback effects, black holes can alter the distribution of baryonic matter in galaxies, which in turn affects the dark matter distribution through gravitational interactions. This creates a three-way connection between black holes, visible matter, and dark matter that shapes the overall structure of galaxies. The quest to observe and understand supermassive black holes has driven some of the most innovative developments in astronomy, pushing the boundaries of technology and human ingenuity. From the first indirect evidence to the stunning direct images captured by the Event Horizon Telescope, each breakthrough has revealed new aspects of these cosmic giants while raising new questions about their nature and behaviour. The earliest evidence for supermassive black holes came from observations of galactic nuclei that showed unusual activity. In the 1960s, astronomers discovered quasars, quasi-stellar radio sources that appeared as point-like objects but showed enormous redshifts, indicating they were billions of light-years away. For such distant objects to be visible, they had to be incredibly luminous, outshining entire galaxies despite originating from regions no larger than our solar system. The only known mechanism that could produce such enormous energy from such a compact region was accretion onto a supermassive black hole. Radio astronomy played a crucial early role in black hole detection. Radio telescopes revealed jets extending from galactic nuclei, narrow beams of emission stretching for millions of light-years. The base of these jets pointed back to incredibly compact sources, regions so small they could only be resolved using very long baseline interferometry, a technique that combines signals from radio telescopes separated by thousands of kilometers to achieve extraordinary angular resolution. These observations showed that the jet launching regions were smaller than a light-year across, consistent with the vicinity of a supermassive black hole. Optical spectroscopy provided another line of evidence. By analysing the light from galactic nuclei, astronomers could measure the velocities of orbiting gas clouds through the Doppler shift of spectral lines. In many galaxies, gas near the centre was moving at velocities of thousands of kilometres per second, far faster than could be explained by the gravitational pull of visible stars. The implied central masses were millions or billions of times the mass of the Sun, concentrated in regions too small to be star clusters. The launch of space-based observatories opened new windows for black hole detection. X-ray telescopes like Chandra and XMM Newton could observe the million-degree gas in accretion disks, revealing the intense heating that occurs as matter spirals toward the event horizon. These observations showed characteristic features like ion emission lines, broadened and skewed by relativistic effects near the black hole. The shape of these lines provided information about the black hole's spin and the geometry of the accretion flow. Infrared observations proved crucial for studying the supermassive black hole at our galaxy's centre. The galactic centre is hidden behind thick clouds of interstellar dust that absorb visible light, but infrared radiation can penetrate this veil. Using adaptive optics to correct for atmospheric blurring, ground-based telescopes like Keck and the Very Large Telescope began tracking individual stars orbiting the galactic center. Over years and decades, astronomers mapped out complete orbits, watching stars swing around an invisible object at incredible speeds. One star, called S2 or S02 depending on the research group, became particularly famous. This star completes an orbit in just 16 years, approaching within 17 light hours of the galactic center at its closest pass. At this point, it reaches speeds exceeding 5,000 kilometers per second, about 2% of the speed of light. The precision tracking of S2 and other stars provided irrefutable evidence for a black hole of 4 million solar masses at the position of the radio source Sagittarius A star. These observations went beyond simple detection, providing tests of Einstein's general relativity in the strong gravitational field near a supermassive black hole. As S2 passed close to the black hole in 2018, astronomers detected gravitational redshift of its light, exactly as predicted by general relativity. They also observed Schwarzschild precession, a gradual rotation of the star's orbital ellipse caused by the curved spacetime near the black hole. These measurements confirmed that gravity near supermassive black holes behaves exactly as Einstein's theory predicts. Reverberation mapping emerged as a powerful technique for measuring black hole masses in distant galaxies. This method exploits the fact that emission from the accretion disk varies over time. When the disk brightens, the increased radiation causes surrounding gas clouds to brighten in response, but with a time delay corresponding to the light travel time. By measuring these delays for gas clouds at different distances, astronomers can map the structure of the region around the black hole and determine its mass from the orbital velocities of the gas. This technique has been applied to hundreds of active galactic nuclei, building up a census of black hole masses across cosmic time. The observations show that supermassive black holes were already in place when the universe was less than 1 billion years old, with some reaching billions of solar masses. This rapid early growth remains one of the puzzles in black hole research, challenging our models of how these objects form and evolve. Gravitational wave astronomy opened an entirely new way to study black holes. While the current generation of gravitational wave detectors, like LIGO and Virgo, can only detect stellar mass black hole mergers, future space-based detectors, like LISA, will be sensitive to the gravitational waves from merging supermassive black holes. These observations will provide precise measurements of black hole masses and spins, revealing the merger history of supermassive black holes across cosmic time. The Event Horizon Telescope achieved what many thought impossible, directly imaging the shadow of a supermassive black hole. This Earth-sized virtual telescope, created by linking radio observatories around the world, achieved the angular resolution necessary to resolve structures on the scale of event horizons. The first target was M87 star, the supermassive black hole in the giant elliptical galaxy Messier 87, chosen because of its enormous mass of 6.5 billion suns and relatively close distance of 55 million light-years. The image, released in April 2019, showed a bright ring of emission surrounding a dark shadow, exactly as predicted by general relativity. The ring is the image of the accretion disk, its light bent and magnified by the black hole's gravity. The dark shadow in the center is caused by the event horizon and the light-bending effects of the black hole's gravity, creating a region from which no light reaches us. The asymmetry in the ring's brightness is caused by Doppler boosting, with the side of the disk rotating toward us appearing brighter. The Event Horizon Telescope later imaged Sagittarius A star, our galaxy's central black hole. Despite being much closer than M87 star, Sagittarius A star was a more challenging target because it's much smaller and varies on shorter timescales. The image released in May 2022 showed similar features to M87 star, but with more rapid variability, confirming that we're seeing emission from very close to the event horizon. These images did more than confirm the existence of event horizons. They provided new ways to test general relativity and measure black hole properties. The size of the shadow depends on the black hole's mass and spin, while its shape can reveal whether the black hole is described by the Kerr solution of general relativity or requires modified theories of gravity. So far, the observations are perfectly consistent with Einstein's theory. Polarimetric observations have added another dimension to black hole studies. By measuring the polarization of light from accretion disks and jets, astronomers can map magnetic field structures around black holes. The Event Horizon telescope's polarized images of M87 star revealed organized magnetic fields near the event horizon, possibly in a configuration called a magnetically arrested disk, where magnetic pressure regulates the accretion flow. Multi-messenger astronomy, combining electromagnetic observations with gravitational waves and neutrinos, promises to revolutionize black hole studies. When supermassive black holes merge, they should produce both gravitational waves detectable by LISA and electromagnetic signals from the disruption of their accretion disks. Simultaneous observations across different messengers will provide unprecedented insights into black hole physics and the environments around merging systems. Time domain astronomy has revealed the dynamic nature of supermassive black holes. Survey telescopes that repeatedly image large areas of sky have discovered numerous transient events associated with black holes. Tidal disruption events, where stars are torn apart by black holes, appear as sudden brightenings that fade over months. Changing look quasars transition between different spectral types on timescales of years, possibly due to changes in accretion rate or disk structure. These observations show that supermassive black holes are not steady-state objects, but dynamic systems with rich variability. Machine learning and artificial intelligence are increasingly being applied to black hole observations. These techniques can identify subtle patterns in complex datasets, classify different types of active galactic nuclei, and even help reconstruct images from interferometric data. As astronomical datasets grow exponentially larger, these computational methods become essential for extracting scientific insights from observations. Throughout the cosmos, certain supermassive black holes have become celebrities in their own right, each one teaching us something unique about these gravitational giants. Their individual stories, from the gentle giant at our galaxy's heart to the most distant quasars at the edge of the observable universe, weave together to form our understanding of black hole physics and evolution. Sagittarius A star, the supermassive black hole at the centre of our Milky Way, holds a special place as our nearest supermassive neighbour. At a distance of just 26,000 light-years, it's close enough that we can study it in exquisite detail. With a mass of 4.3 million suns, it's relatively modest by supermassive standards, but this proximity makes it our best laboratory for understanding black hole physics. The story of Sagittarius A star's discovery is a testament to astronomical persistence. The galactic centre had long been known to harbour something unusual, detected as a bright radio source as early as the 1970s. But proving this source was a black hole required decades of patient observation. Astronomers had to develop new techniques to peer through the dense veil of dust that obscures the galactic centre in visible light, turning instead to infrared observations that could penetrate this cosmic fog. What makes Sagittarius A star particularly fascinating is how quiet it is. Despite having plenty of hot gas in its vicinity, it accretes at only about 100 millionth of the Eddington rate, making it underluminous by a factor of 1 billion compared to what it could theoretically achieve. This quiescence puzzled astronomers for years. Why wasn't our black hole feeding more actively? The answer appears to lie in the nature of the accretion flow, which is so hot and diffuse that most of the energy is carried into the black hole rather than radiated away. Occasionally, Sagittarius A star shows flares, brightening in X-rays, and infrared by factors of 10 to 100 for periods of tens of minutes to hours. These flares might be caused by magnetic reconnection events in the inner accretion flow, or by small clouds of gas falling into the black hole. In 2013 and 2014, astronomers watched with great anticipation as a gas cloud called G2 made a close approach to the black hole. Many expected dramatic fireworks as the cloud was torn apart and consumed, but surprisingly, G2 survived its encounter largely intact, suggesting it might have been a star shrouded in gas rather than a simple gas cloud. The recent observations by the James Webb Space Telescope have revealed new details about Sagittarius A star's flaring behaviour. Webb detected both faint flickers and brighter flares in the mid-infrared, providing unprecedented detail about the accretion disk's variability. These observations allowed astronomers to estimate that the black hole's magnetic field is about 100 times stronger than Earth's magnetic field, a crucial measurement for understanding how matter behaves in the extreme environment near the event horizon. The flares from Sagittarius A star follow patterns that astronomers are still working to understand. Analysis of 15 years of data shows that the black hole flashes every day, with bursts of radiation 10 to 100 times brighter than its quiescent state. The flares appear to originate from synchrotron emission, produced when electrons are accelerated to near light speed along magnetic field lines, possibly triggered by magnetic reconnection events where field lines approach each other and suddenly reconfigure. Moving beyond our galaxy, M87 star stands as perhaps the most famous supermassive black hole in astronomy, earning its celebrity status by becoming the first black hole ever directly imaged. Located 55 million light-years away in the giant elliptical galaxy Messier 87, this monster weighs in at 6.5 billion solar masses, making it one of the most massive black holes in the local universe. M87 star has been known to be special since the early 20th century, when astronomers first noticed a peculiar jet emanating from the galaxy's centre. This jet, visible even in optical telescopes, extends for 5,000 light-years, a cosmic blowtorch powered by the black hole's rotation and magnetic fields. The jet moves at relativistic speeds, with knots of emission appearing to travel faster than light due to projection effects, a phenomenon called superluminal motion that provided early evidence for the extreme physics at play. The Event Horizon Telescope's image of M87 star revealed not just the black hole's shadow, but also the structure of the accretion flow in unprecedented detail. The bright ring in the image has a diameter of about 42 microarc seconds, corresponding to a physical size of about 100 billion kilometers. The ring's brightness is asymmetric, with the bottom portion appearing brighter due to Doppler boosting from material moving toward us. This asymmetry allowed astronomers to determine that the black hole is rotating clockwise as seen from Earth, and that we're viewing the system from a slight angle above the accretion disk. Subsequent polarized observations of M87 star revealed the magnetic field structure near the event horizon. The polarization patterns showed organized magnetic fields threading the accretion flow, possibly in a configuration called a magnetically arrested disk, where magnetic pressure becomes strong enough to regulate the accretion rate. These magnetic fields are crucial for launching and collimating the jet, extracting energy from the black hole's rotation through the Blandford-Znajek mechanism. The quasar 3C273, discovered in 1963, holds the distinction of being the first quasar ever identified and remains one of the brightest quasars in Earth's sky, despite being 2.5 billion light-years away. Its supermassive black hole, with a mass of about 900 million suns, powers a luminosity equivalent to 2 trillion stars. The quasar's jet extends for hundreds of thousands of light-years, visible across the electromagnetic spectrum, from radio waves to gamma rays. What makes 3C273 particularly valuable for research is its brightness and relative proximity compared to other quasars. It's bright enough that even amateur astronomers with modest telescopes can observe it, appearing as a 13th magnitude star. Professional astronomers have studied it across every wavelength band, building up one of the most complete pictures we have of a quasar system. Observations show dramatic variability on timescales from days to years, providing insights into the structure and dynamics of the accretion disk and jet. The binary black hole system OJ287 presents one of the most extraordinary supermassive black hole configurations known. Located 3.5 billion light-years away, this system consists of a primary black hole of 18 billion solar masses, orbited by a secondary black hole of 150 million solar masses. The secondary black hole completes an orbit every 12 years, passing through the primary's accretion disk twice per orbit and creating predictable optical flares that have been observed for over a century. These flares occur with such regularity that astronomers can predict them years in advance, though general relativistic effects cause the timing to shift slightly with each orbit. The system provides a unique laboratory for testing general relativity in the strong field regime. Observations of the orbital decay due to gravitational wave emission match theoretical predictions precisely, and the system shows measurable frame-dragging effects from the primary black hole's rotation. TON 618 represents the extreme end of black hole masses, harbouring one of the most massive black holes ever discovered at 66 billion solar masses. Located 10.5 billion light-years away, this ultramassive black hole powers one of the most luminous quasars known, with a luminosity of 4 × 10 to the 40th watts, equivalent to 140 trillion suns. The black hole is so massive that its event horizon would engulf the entire orbit of Pluto many times over. The existence of such ultramassive black holes challenges our understanding of black hole growth. Even starting from a massive seed and accreting continuously at the Eddington limit, growing to 66 billion solar masses in the available time is barely possible. This suggests that TON 618 might have experienced periods of super Eddington accretion or formed through the merger of multiple already massive black holes. The most distant quasar currently known, J0313d1806, showcases a supermassive black hole that existed when the universe was only 670 million years old, just 5% of its current age. Despite this early epoch, the black hole already had a mass of 1.5 billion suns, presenting a severe challenge to models of black hole formation. The quasar's light has travelled for over 13 billion years to reach us, providing a window into the universe's infancy. The spectrum of J0313d1806 reveals a universe very different from today. The intergalactic medium was still partially neutral, with the epoch of Ryanization ongoing. The quasar's host galaxy was forming stars at a rate of 200 solar masses per year, about 100 times faster than the Milky Way today. The presence of dust and heavy elements in the galaxy shows that significant stellar evolution had already occurred, despite the universe's youth. NGC 4889's black hole represents another extreme, with a mass estimated between 9 and 37 billion solar masses, making it one of the most massive black holes in the local universe. Located 300 million light-years away in the Coma cluster, this black hole now lies dormant, having consumed or expelled all available gas in its vicinity. The galaxy itself is a giant elliptical, likely formed through multiple major mergers that would have fed the black hole's growth. The range in the mass estimate for NGC 4889's black hole illustrates the challenges in measuring black hole masses. Different techniques, including stellar dynamics, gas dynamics, and scaling relations, give somewhat different results. The true mass likely lies somewhere in the middle of the range, around 20 billion solar masses, but the uncertainty highlights how much we still have to learn about these extreme objects. Markarian 231, the nearest quasar to Earth at 600 million light-years, hosts not one, but two supermassive black holes. The primary black hole has a mass of 150 million solar masses, while the secondary weighs in at 4 million solar masses. The two black holes orbit each other with a period of about 1.2 years, and their orbital motion creates gaps in the accretion disk that affect the observed spectrum. This binary system likely formed from a galaxy merger, with each black hole being the remnant of its parent galaxy's central black hole. The two black holes will eventually merge, producing gravitational waves detectable by future space-based observatories. The merger will create a single, more massive black hole, possibly ejecting it from the galaxy center due to gravitational wave recoil. The Phoenix cluster's central black hole showcases extreme feedback in action. Located 5.7 billion light-years away, this black hole of 20 billion solar masses sits at the center of one of the most massive galaxy clusters known. The black hole's jets have inflated enormous cavities in the hot cluster gas, each cavity large enough to contain hundreds of Milky Way galaxies. Yet despite this powerful feedback, the cluster still shows the highest rate of cooling and star formation of any known cluster, suggesting a delicate balance between heating and cooling. Near a supermassive black hole, the fabric of space-time becomes so warped that our everyday understanding of physics breaks down completely. Time flows differently, space curves in impossible ways, and the very concepts of now and here lose their absolute meaning. These relativistic effects aren't just theoretical curiosities, but observable phenomena that shape everything from the appearance of accretion disks to the trajectories of orbiting stars. The gravitational time dilation near a supermassive black hole creates a cosmic time machine of sorts. As you approach the event horizon, time slows relative to the outside universe. For a billion solar mass black hole, standing at the innermost stable circular orbit would mean that for every hour that passes for you, about an hour and 15 minutes pass for someone far from the black hole. This might seem like a modest effect, but it has profound consequences for our observations of black hole systems. This time, dilation affects everything we observe near black holes. Light emitted from the inner accretion disk is gravitationally redshifted, its wavelength stretched as it climbs out of the gravitational well. A photon, emitted with a specific energy near the black hole, arrives at our telescopes with less energy, shifted toward the red end of the spectrum. For light emitted very close to the event horizon, this redshift can be extreme, with visible light shifted all the way into the infrared or beyond. The combination of gravitational redshift and Doppler effects from orbital motion creates complex spectral signatures in the light from accretion disks. Iron atoms in the disk emit X-rays at a very specific energy, 6.4 kilo-electron-volts, creating what should be a sharp spectral line. But when we observe this line from black hole accretion disks, it's broadened and skewed into a characteristic shape. The approaching side of the disk is blue-shifted and brightened, while the receding side is red-shifted and dimmed. Gravitational redshift affects the entire line, with emission from closer to the black hole shifted more than emission from farther away. These iron lines have become one of our most powerful tools for studying black hole spacetime. By modelling the line shape, astronomers can determine how close the disk extends to the black hole, which tells us about the black hole's spin. A disk extending very close to the horizon indicates a rapidly spinning black hole with a small innermost stable circular orbit. The line profile also reveals the inclination angle of the disk and can even show evidence for warping or precession of the disk plane. Light bending or gravitational lensing near black holes creates some of the most striking visual effects. Light rays passing close to a black hole are deflected by the curved spacetime, with rays that pass closer being bent more strongly. This means that we can actually see parts of the accretion disk that should be hidden behind the black hole. The far side of the disk appears as a bright arc, above and below the black hole's shadow, creating the characteristic appearance seen in the Event Horizon Telescope, images, and countless scientific visualizations. For a maximally spinning black hole, these lensing effects become even more extreme. Light can orbit the black hole multiple times before escaping, creating multiple images of the same source. In principle, we could see an infinite series of increasingly demagnified images of the accretion disk, though in practice only the first few are bright enough to detect. These higher-order images appear as thin rings just outside the black hole's shadow, each one showing the disk at an earlier time, due to the longer light travel path. The dragging of spacetime by a rotating black hole, known as frame dragging or the lens-thering effect, creates some of the most exotic phenomena in black hole physics. Near a rapidly spinning, supermassive black hole, space itself is twisted into a whirlpool-like configuration. Any object near the black hole is carried along by this swirling space-time, forced to rotate with the black hole regardless of its initial motion. This frame dragging has observable consequences for accretion disks and jets. A disk that's initially misaligned with the black hole's rotation will experience differential precession, with the inner parts precessing faster than the outer parts. This can cause the disk to warp or even tear into distinct rings at different orientations. For jets, frame dragging can help explain their remarkable collimation and stability, as the twisted spacetime naturally channels outflows along the rotation axis. The Penrose process, a mechanism for extracting energy from rotating black holes, exploits the properties of the ergosphere. In this region, the dragging of spacetime is so strong that all particles must rotate with the black hole. A particle entering the ergosphere can split in two, with one fragment falling into the black hole on a retrograde orbit opposite to the black hole's rotation, while the other escapes with more energy than the original particle. The infalling fragment actually has negative energy relative to infinity, reducing the black hole's mass and angular momentum, while the escaping fragment carries away the extracted energy. While the Penrose process is unlikely to operate efficiently for individual particles in real astrophysical situations, magnetic field versions of this mechanism might be responsible for powering jets. The Blandford-Znajek mechanism, a magnetic version of the Penrose process, can extract rotational energy from the black hole through magnetic field lines threading the ergosphere. This process could convert a significant fraction of the black hole's rotational energy into jet power, potentially explaining the enormous energies observed in quasar jets. Relativistic precession affects the orbits of objects around black holes in ways that would seem impossible in Newtonian gravity. The perihelion of an orbit, its closest approach to the black hole, shifts slightly with each orbit due to the curved spacetime. For Mercury orbiting our Sun, this precession amounts to just 43 arc-seconds per century, but near a supermassive black hole, the effect is dramatically amplified. The star S2 orbiting Sagittarius A star shows a precession of about 12 arc-minutes per orbit, a readily measurable effect that confirms general relativity's predictions. The relativistic effects become even more extreme for particles spiraling into the black hole. As matter in the accretion disk loses angular momentum and spirals inward, it experiences increasingly strong relativistic effects. In the plunging region inside the innermost stable circular orbit, particles follow chaotic, non-Keplerian trajectories as they spiral toward the event horizon. The radiation from this region is strongly beamed and gravitationally lensed, creating rapid variability in the observed emission. Relativistic jets from supermassive black holes showcase special relativity on cosmic scales. Matter in these jets moves at speeds exceeding 99% of the speed of light, creating dramatic observational effects. When a jet points toward us, relativistic beaming concentrates the emission into a narrow cone, making the jet appear much brighter than it would at rest. Time dilation means that processes in the jet appear to unfold more slowly than they actually do in the jet's reference frame. Perhaps most remarkably, knots of emission in jets can appear to move faster than light across the sky, a phenomenon called superluminal motion. This isn't a violation of relativity, but rather a projection effect. When a blob of matter in a jet moves almost directly toward us at near light speed, it nearly keeps pace with the light it emits. The light emitted when the blob is farther away has a head start, but the light emitted when it's closer doesn't lag far behind. When we observe these two signals, the blob appears to have traversed the sky faster than light could have travelled that distance. The study of relativistic effects around supermassive black holes has provided some of our strongest tests of general relativity. The theory has passed every test with flying colours, from the precession of stellar orbits to the shape of black hole shadows. But physicists continue to push these tests to ever greater precision, looking for any deviation that might point toward new physics beyond Einstein's theory. Recent observations have even detected the gravitational redshift of light from stars passing close to Sagittarius A star, exactly as predicted by general relativity. As the star S2 made its closest approach to the black hole in 2018, its light was redshifted by about 200 kilometers per second due to the gravitational field. This measurement required exquisite precision and decades of preparation, but it provided a direct confirmation of Einstein's predictions in the strong gravitational field near a supermassive black hole. The extreme physics near supermassive black holes also provides insights into quantum mechanics in curved spacetime. While we can't directly observe quantum effects near astrophysical black holes, the theoretical framework developed to understand these effects has profound implications. The Unruh effect predicts that an accelerating observer sees a thermal bath of particles even in vacuum, and near a black hole, the enormous accelerations required to remain stationary could make this effect significant. The future of supermassive black holes stretches across timescales so vast that they dwarf the current age of the universe, extending into an era when the cosmos will be unrecognizably different from today. These gravitational giants, which seem eternal and unchanging on human timescales, will undergo profound transformations over the eons, ultimately facing a fate that Stephen Hawking's calculations revealed to be both inevitable and almost incomprehensibly distant. In the immediate cosmic future, measured in mere billions of years, supermassive black holes will continue their co-evolution with galaxies. As the universe expands and galaxies drift apart, the rate of galaxy mergers will decline, reducing one of the primary growth mechanisms for supermassive black holes. The cosmic supply of cold gas, The fuel for both star formation and black hole growth will gradually be depleted. Star formation in the universe has already peaked and is now declining, and black hole growth is following a similar trajectory. Our own galaxy's supermassive black hole, Sagittarius A star, will experience dramatic changes when the Milky Way collides with the Andromeda galaxy in about 4.5 billion years. This cosmic collision will bring together two supermassive black holes, Sagittarius A star with its 4 million solar masses and Andromeda's black hole of perhaps 100 million solar masses. The merger won't happen immediately. First, the two galaxies will pass through each other, their spiral structures disrupted and distorted by tidal forces. Gas will be driven toward the center of the merging system, potentially triggering new episodes of star formation and black hole feeding. Over hundreds of millions of years, the two black holes will sink toward the center of the merged galaxy through dynamical friction, as their gravitational influence flings stars outward and causes the black holes to lose orbital energy. Eventually, they'll form a binary system, orbiting each other at distances of a few parsecs. Getting closer requires clearing out all the stars in their orbital path, a process that could take billions of years. This is known as the final parsec problem, and astronomers still debate how black hole binaries overcome this barrier to merge. Once the black holes approach within about 1,000th of a parsec, gravitational wave emission takes over as the dominant mechanism for orbital decay. The binary will spiral together increasingly rapidly, emitting gravitational waves of ever-increasing frequency and amplitude. In the final moments before merger, the black holes will be orbiting each other hundreds of times per second, distorting spacetime so violently that several % of their combined mass is radiated away as gravitational waves in just seconds. The merger itself is one of the most violent events possible in the universe. The two event horizons will distort and elongate toward each other, eventually touching and merging into a single, highly distorted horizon. This new black hole will be born ringing like a struck bell, oscillating in its characteristic quasi-normal modes as it settles down to a stable state. The gravitational waves from this ring down encode information about the final black hole's mass and spin, providing a direct probe of the spacetime structure around the newly formed black hole. If the two merging black holes have unequal masses or spins that aren't perfectly aligned, the gravitational waves will be emitted asymmetrically, imparting a recoil velocity to the final black hole. For certain configurations, this kick can exceed thousands of kilometers per second, potentially ejecting the black hole from the galaxy entirely. Such recoiling black holes would wander intergalactic space, carrying with them any accretion disk or closely bound stars, creating the bizarre phenomenon of a hypercompact stellar system without a host galaxy. As the universe continues to expand and cool, the environment around supermassive black holes will change dramatically. In about 1 trillion years, star formation will have ceased throughout the universe as the supply of gas is exhausted. Galaxies will fade as their stars age and die, leaving behind white dwarfs, neutron stars, and stellar mass black holes. Supermassive black holes will be surrounded by these stellar remnants, occasionally consuming one that ventures too close, producing a brief flare in an otherwise dark universe. The expansion of the universe, accelerated by dark energy, will eventually isolate each galaxy or galaxy group in its own observable universe. Galaxies beyond our local group will disappear beyond the cosmic horizon, their light redshifted to undetectability. Each supermassive black hole will reign over an island universe, unable to merge with distant black holes or accrete intergalactic gas. In this far future, the primary growth mechanism for supermassive black holes will be the occasional capture of stellar remnants and the very slow accretion of the cosmic microwave background radiation. As the universe expands, the cosmic microwave background will cool from its current temperature of 2.7 Kelvin toward absolute zero. But even this incredibly cold radiation carries energy, and black holes will absorb it, growing imperceptibly slowly. On even longer timescales, the quantum mechanical process of Hawking radiation becomes important. Black holes aren't perfectly black, but emit a faint thermal radiation due to quantum effects near the event horizon. The temperature of this radiation is inversely proportional to the black hole's mass, so supermassive black holes are the coldest objects in the universe. A billion solar mass black hole has a Hawking temperature of only 60 trillionths of a degree above absolute zero. Currently, supermassive black holes absorb far more energy from the cosmic microwave background than they emit through Hawking radiation, causing them to grow rather than evaporate. But as the universe expands and cools, there will come a time when the cosmic microwave background temperature drops below the black hole's Hawking temperature. At this point, the black hole will begin to evaporate, losing mass through Hawking radiation. The evaporation process is extraordinarily slow for supermassive black holes. The time for a black hole to evaporate completely scales as the cube of its mass. A billion solar mass black hole would take about 2 times 10 to the 100th power years to evaporate, a number so large it defies comprehension. Written out, it would be a 2 followed by 100 zeros, vastly longer than the current age of the universe, longer than the time until all stars have died, longer than the time until all protons have potentially decayed. As a black hole evaporates, it becomes hotter and radiates faster. In its final moments, it would release enormous amounts of energy in a violent explosion. But for supermassive black holes, these final moments are separated from the present by spans of time that render all of cosmic history so far as less than an eye blink. During the evaporation process, the black hole's radiation carries away not just mass but also information about what fell into the black hole. This leads to the black hole information paradox, one of the deepest puzzles in theoretical physics. Quantum mechanics says information cannot be destroyed, but general relativity suggests that information falling into a black hole is lost forever. The resolution of this paradox might require a quantum theory of gravity, potentially revolutionizing our understanding of space, time, and information. Some theories suggest that black holes might not evaporate completely, but leave behind Planck-scale remnants, tiny objects with the mass of a dust grain, but the entropy of a supermassive black hole. These remnants would be stable, preserving the information that fell into the black hole, but encoding it in a form we don't yet understand. If such remnants exist, they would be the final legacy of supermassive black holes, eternal monuments to the gravitational giants that once powered quasars and shaped galaxies. Other speculative theories propose even stranger fates for black holes. Some models of quantum gravity suggest that black holes might transition into other objects, perhaps white holes that expel matter rather than absorbing it, or naked singularities that would expose the universe's most extreme physics to outside observation. While these ideas remain highly speculative, they illustrate how much mystery still surrounds the ultimate fate of black holes. The far future evolution of supermassive black holes is intimately connected to the fate of the universe itself. If dark energy continues to accelerate cosmic expansion, the universe will become increasingly cold and empty, a state physicists call heat death. Black holes will be among the last objects to survive in this dying universe, their Hawking radiation providing the final sources of energy in an otherwise frozen cosmos. But if dark energy changes over time, perhaps decreasing or even reversing sign, the universe's fate could be very different. The expansion might slow and reverse, leading to a big crunch where all matter and black holes merge into a single, universe-encompassing singularity. Or dark energy might increase, leading to a big rip where even black holes are torn apart by the accelerating expansion of space itself. Recent observations suggest that supermassive black holes might play a role in dark energy itself. Some theories propose that black holes could be the source of dark energy, with their interiors containing exotic energy that drives cosmic acceleration. If true, this would mean that supermassive black holes aren't just shaped by cosmic evolution, but actively drive it, making them even more fundamental to the universe's structure and fate than we currently imagine. As we reach the end of our cosmic journey through the realm of supermassive black holes, we find ourselves standing at the edge of human knowledge, peering into mysteries that challenge our understanding of reality itself. These gravitational titans, born in the universe's youth and destined to outlive the stars by unimaginable eons, have revealed themselves to be far more than mere cosmic vacuum cleaners. They are architects of galaxies, laboratories of extreme physics, and perhaps even keys to understanding the fundamental nature of space, time, and information. From the patient observations of stars orbiting invisible masses to the stunning images captured by the Event Horizon Telescope, our quest to understand supermassive black holes has pushed the boundaries of human ingenuity and technology. Each discovery has answered some questions while raising new ones, maintaining the sense of wonder that drives scientific exploration. The story of supermassive black holes is far from complete, with new chapters being written by astronomers and physicists around the world every day.